something so adorable about her getting into the little house to get a peanut. I just moved the water over there. You aren't that dumb, are you? I made a little cup holder with the wire and strap it so it's nice. But
In case anybody's wondering, my wife's talking about her squirrel restaurant chez Jennifer. Apparently, the squirrel is unhappy with the
with the
offerings.
arrangements.
Well, we don't have any ads to start off today. Okay, that's fine. Welcome, welcome, everybody, to another edition of The Tutor Wizard today. This is Introduction to Statistics, lecture number 13. I'm Tim, and today's kitty is Willa, a big, fluffy tuxedo cat who has a very loud motor. Not as loud as Petra, who you'll meet sooner than later, but today's lucky charm cat, Willa, is pretty sweet with some pretty excellent pantaloons, too. So it's all good. It's all good. What are we doing today in lecture number 13? We're going to continue on with hypothesis testing for proportions. We're going to look at the two sample technique for that. And then we're going to slide on over to chi-square tests, which should wrap up proportions until we do some reviews for the final exam. So with that in mind, we should probably get busy, because I have yard work to do today. I have construction work to do. I'm trying to put up a shed that I took apart about a month ago. And to be honest with you, I've kind of forgotten how it came apart, so putting it back together is going to be an exercise in, I think this goes here, but I could be wrong. Anyway, I'm sure you'll hear all about it. But we have some unfinished business. From lecture number 12, I said I would review the one question, make sure I had the right answer, and it is correct, but let's just summarize from lecture 12. We did a confidence interval. It was a two-sample confidence interval. The difference between the two samples was 3 percentage points, which is what you see here. And it was at 90%, so this is our critical value, 1.645, and the standard error was 0.1339. That produced an interval that spanned 0, hence there was no significant difference, ranged from negative 19 percentage points to positive 25 percentage points. So the second part of that question was, let's determine the critical value for z that would change the insignificant result to a significant result. Now, if you recall, I had said I had worked out the solution, just doodled it on paper, but when I doodled it on the stream, I got a totally different answer. So to clarify which one was correct, I redid it today, and the one I did on the stream yesterday was the correct answer. It's ridiculously small, by the way, as you're going to see right now. So, and then we're going to come up with a new confidence level. So the mathematics ultimately came down to, we had to find z star, the critical value of z. That would be, I got that arrow going the wrong way. Darn it. Okay. No, that's right. So z has to be beyond, or pardon me, less than 0.03. Now, when you solve that, you end up with 0.22. Well, 22 and a little bit of change, but it doesn't really matter. Now, the point is, this is z star of negative 0.22 here, and this is positive 0.22 here. Now, when you look this up on the z table, you find that this region is 0.4129, and of course, confidence intervals are symmetric, so there's another 4129 over here. Well, if you add those two together, it doesn't leave a lot left over. That works out to 0.8258. So the remaining value, 1742, constitutes the center, and that's our confidence region, which is for all intents and purposes 17% confidence. So we did it right yesterday. It was just a matter of, well, when you have two different answers, you have to do it the third time to find out which one's correct. Okay, that's enough of that. Let's move on. Okay, let's talk about two-sample hypothesis testing using proportions. So the formula we need is this bad boy right here. As always, for two-sample tests, the numerator is simply the difference between the two measured or calculated proportions. The denominator is the standard error, and it has a complicating factor, and you'll notice that we have PC here. So I'm using the subscript C to say combined. Now some formula sheets have it written like this. Some will have a hat on the P. It doesn't really matter. The point is we have to use either this formula or this formula to find the weighted average of the two proportions. And you're going to see that coming up here in a few moments. Now, if they give you the success count, you do this one here, because this would be the sum of the success counts in the numerator and then the sum of the total sample sizes in the denominator. That's the easy way. If they only give you sample size and the measured proportion, then you have to multiply your p-hats by the sample sizes, which essentially is undoing the computation to get the success count, and then add them up and divide as you see here. So this one here is simply the success count divided by the total. That's the easy one. The second one, like I said, you have to work the percentages backwards and then do the division. It's not the end of the world, though. But just keep in mind, you have to do that. The only time that you really don't need to do that, and you can just take the average of the two p-hats, is if the sample sizes are the same, because then you don't have to worry about a weighted average. But that rarely occurs in reality, so these two formulas get used quite a bit. Now, what are the hypotheses for a two-sample proportion? Let's have a look at that. Well, I don't have my, hang on here, I'm not properly accoutrement. My laptop's an older one, so the screen is sensitive to skin touch and didn't have my art glove on, which is really just a glove liner. Okay, what are the hypotheses for this? Well, the null hypothesis is going to be P1 or P sub 0, 1. I'm going to use the subscript null, P, for the population value. And this will be 0, because remember, if two things are essentially the same and you subtract them, you should get 0. The alternative hypothesis, that's supposed to be an A, Tim, there we go, is again non-zero. Now, what that's going to be depends on the question. Either be a two-tail test, when it does not equal 0, it'll be less than 0, or greater than 0. So this is what we talked about. This is basically the same as what we talked about earlier when we were looking at one-sample hypothesis testing. We're only going to chase down significance with p-values in this discussion. I'm going to save the use of critical values for when we get to working with means in the next few lectures, because with the t-table being a cutoff table, it can be done either way just as easily. But with proportions, because we have access to the z-table, we can get p-values quite easily. Anyway, that'll come up. So significance with p-values, just a reminder for everyone that if you're not told what the significance level is, so you're going to default to 5% unless you have a reason otherwise. Now, this can also be 10%. This can also be 1%. Technically, you can set this to whatever you want it to be, whatever the situation requires it to be. but you should have a reason for doing so. And if you want to think about that, go back to not the last discussion, I think it was the previous lecture from two back. We were talking about type 1 and type 2 errors, and you want to consider which is going to lead to the least harm. If in the case of are you getting a false positive or a false negative, which one causes the worse outcome, would influence your decision as to what you'd set the level of significance to. I'm not going to rehash that entire discussion. Just go back and review that stream if you wish. Let's move on to our first example. What we want to do here is compare the survival rates between two experiments and determine if a significant difference exists. Okay. I'm going to move this up a little bit so we have some room. Again, we're using the correct formula, and we have this. And I've included an excerpt from the Z table down here in the lower right. And provided I don't mess up the computation, that should be all we need. So experiment 1 had 30 subjects. The survival rate was 32%. Experiment 2 had 40 subjects. Survival rate there was 35%. We're going to use significance at 1%. Now remember, we need the weighted average of the percentages. And since the two sample sizes are not the same, we need to use a computation. Now you'll notice that I have p hats here. Survival, this is going to be p hat 1, and this is going to be p hat 2. So if you didn't use the formula, you would say, well, it's going to be halfway in between, it'll be 33.5. And if the sample sizes were the same, that would be correct. But they're not. How do you know you've done it right? Well, I can't guarantee you've done it right, but you can get a quick judgment. The combined proportion will be closer to the percentage that's associated with the largest of the two samples. So here I would expect probably our combined proportion to be somewhere around 0.34, which is closer to 0.35 than it is to 0.32. Let's figure it out. Now, I didn't give the survival counts, so we're going to use this formula right here. So P sub C. So P hat 1 was 0.32. We're going to multiply that by 30. For P hat 2, we had 0.35. And we'll multiply that by 40. The total sample sizes were 30 and 40, so the denominator is an easy 70. Now let's work out the numerator. Now normally you'd probably want to carry 4 decimals all the way through these computations. I'm only going to carry 2 due to lack of space, and I'm not interested so much in, did I get the right decimal right in the 5th place? I just want you to see how the heck to do these things. So we got 0.32 times 30 plus 0.35 times 40, and I get 23.6. So that is the success count. Now what is this in terms of a percentage? I'm going to divide that number by 70, and I get 3371. So this is 3371. So I'm going to round that to 0.34 and call it good enough for our example here today. But you'll notice if it was perfectly, if we just took the average of the two p hats, we would have had exactly 0.335. But because experiment number 2 has a larger sample size, we end up with something slightly larger than 0.335, as it should be. Okay, with that in mind, we can set up our Z formula. So Z, well, now how do I want to subtract this? I am going to go P2, P hat 2 minus P hat 1, because I just want to avoid the negative sign. It doesn't really matter in context here. I haven't done the hypotheses yet, but we'll get to that in a minute. So here we're going to have 0.35 minus 0.32. There's our numerator. Now, under the root in the denominator, I need PC, and I said that's 0.34. Now, 1 minus that would be 0.66. And then we have 1 over 30 and 1 over 40. And that's our standard error. So what does this work out to? Well, the numerator is 3 percentage points. Let's get the denominator now. I'm going to do that all in one computation. So, break out trusty calculator, 0.34 times 0.66. And I'm going to multiply by an open bracket. 1 divided by 30 plus 1 divided by 40. And close the bracket and then close your square root and hit enter. And this works out to 0.1144. So as far as the z-score goes then, we take our numerator, 0.03, and divide it by our standard error for a ridiculously small value of 0.26. There's only 2 decimals on the table, so that's all right. It's actually 2622, but since the table only has 2 decimals, that's good enough for us. So there's our z-score. Now let's take a look at the p-value. So let's look over here at our table. Let's get the highlighter in action today. Let's use green. Okay, so here's 0.2, and we need to go all the way over to column 6 and then up. So we're interested in this value right there, 6026. However, take note that is where the p-value refers to. That's all the area to the left of our z-score. But that's not what we need for an answer. When we're doing these hypothesis tests, unless something is specifically set up to want all that area to the left, what we really want then is the area to the right. We need this tail here. This is what we want. We want this. And the way we're going to get it is go 1 minus this value. So the p-value is going to be 1 minus 0.6026, and that should be 0.3974. So regardless of what the level of significance is, this thing is huge when we compare the two. So there's really nothing significant going on, but I am going to list the hypotheses anyway, because that's what we need to do to talk about this in a full and complete manner. So let's get a little bit of room here. Move this up a little bit. There we go. Okay, so the null hypothesis, as we talked about in the previous, was p null for number 2 minus p null for number 1 was equal to 0. And the alternative would have been this. Now, I said, is there a difference? And that means this is a does not equal sign. I didn't prejudge it to be larger or smaller. I just asked if it's different, a different survival rate. And because this is a does not equal sign, that makes this a two-tailed test. And the way we usually do it is to multiply the p-value by 2. And if we do that, that's going to be very large. That's going to be, what the heck is that? That's going to be almost 80%. That's going to be 78, 79, 8. Oh, my battery's almost toast on my calculator. Lovely. Luckily, I have 2 of these. So we got 0.3924 times 2. We get 7848. Now, You got to compare that to alpha. Well, alpha is 1%, so yeah, this is huge. So since the p-value is much larger than alpha, we fail to reject the null hypothesis. As far as the data is concerned, there's no real difference in survival rates here. And when we think about it, that kind of makes sense. Given the size of the samples and only a 3 percentage point difference in survival rate, yeah, not much going on there. Now, if those samples had been 300 and 400 respectively, things might have been different. But they're not, and that's all there is to this example, really. So there's one of the ways we have to interact with this formula. What? Sorry, gotta get this one back over here. Specifically, this formula showed, or this example showed us how to use this computation. Now let's go to the next slide and see how the other one works out here. I'm just going to check something on OBS. Let's just flip back over here for a minute. Yeah, no, we're still working fine. Okay, I was wondering about that. So now, here's another. Public opinion surveys on the north side of the city showed that 44 people out of 200 approved of a particular construction project, while on the south side, 65 people out of 150 respondents approved of the project. Here I'm asking, does the south side have a higher approval rate? Well, let's find out. And let's set this up. Where can we make the hypothesis? I've got a bit more room on this page. So let's do that here. So the null hypothesis is that, now if I'm asking is the approval rate on the south side higher than the approval rate on the north side, and if I want to avoid a negative sign, which I do, well, you know what, screw it. We're gonna just go with the negative sign then. We're gonna go p null for the north side minus p null for the south side. Again, the null hypothesis is that there's no difference, and the alternative is that, now this is actually a good one to talk about, p null minus p null for the south side. Now you may think, oh wait, you got to put a greater than sign in there, but no we don't. Remember, I'm asking, does the south side have a higher approval rate? Well, now this one might actually have made sense to switch those around. So we want to know, is the south side higher? Well, first off, we should probably find out what the p-hats are. See, sometimes you have to think about these things out of order. So south side, 44 out of 200, that's an easy 0.22. But here on, or pardon me, that was the north side. What the hell am I doing here? Do 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 do. Now, yeah, no, that's busy talking, not thinking. Let's just back that out. North side, that's an N, 0.22. Now, here on the south side, what do we have? Where am I going to write that? Let's do this over here. So p hat for this one is 65 out of 150, and I think that's around 30-some%. Let's find out. 65, well, it'll be more than that actually, 150. That's 43%. Don't trust my math today. There we go, 0.43. Okay, so we want to know, does the south side have a higher approval rate? Oh, this is a small value. This is a large value. And when you subtract a large number from a small number, you get a negative sign. So that's why we're going to put a negative symbol, less than 0, in there. So you got to watch out for that. Words can tangle you up on this stuff. And you wouldn't be the first person to get that hypothesis inequality wrong. I almost got it wrong there myself, and I wrote the question, so what does that tell you? Okay, now we got to find PC. Well, let's get PC here. Now here we have the success conditions. I said 44 out of 200. Okay, so now we're going to use this formula here. So here's 44 out of 200. Now on the south side we had 65, and that was out of 150. So the denominator is 350 respondents, and the numerator is 109. So we need to know what that works out to. 109 divided by 350 is 31%. It's 0.311, so that's why I'm just going to go to 0.31. There we go. Now, you'll notice that that is closer to the north side sample proportion because that's the larger of the two samples. This is 9 percentage points away from 0.22, but it's 12 percentage points away from 0.43. Anyway, we have everything we need. Let's set this up. So here we have Z, and we're going to just leave it the way it is. We're going to go north side 0.22 minus south side 0.43. And in the denominator, under the square root, we need 0.31. Now we got to multiply that by 1 minus, so that's going to be 0.69. And then in brackets, 1 over the sample sizes added. So in the numerator, we have negative 0.21. And the denominator is calculator work. 0.31 times 0.69. Then we open a bracket, go 1 divided by 200, and 1 divided by 150, and we get that, and we take the square root of that, and we get 0.04995. Well, you know what? That's so close. That rounds to. We're not going to do that one. We're gonna use 0.05 because why the hell wouldn't you, right? So, what's our z-score? Our z-score will be negative 0.21 divided by 0.05, and we get negative 4.2. So we're 4.2 standard deviations below the mean. Now, you'll notice here, because I changed my mind from what I did when I set this up, this is an excerpt from the positive table. But I'm going to explain how we can get this in the same manner. As remember, the normal distribution curve is symmetric around the center. So if we think about z at positive 0.42, and we look here, well, the z tables typically end, here is 3.9, and I'm already at 100%. So that means the region here is essentially 0. But this is negative. So now I'm interested in this little slip over here, negative 4.2. Well, if the area up here is 0, then the area in this region, all through here, is 1. Well, that means this area here is essentially 0 as well, because these curves are symmetric around the center. So if the upper tail is essentially 0, then the lower tail is essentially 0. So the p-value, with software, it'll give you the exact value. If you want, I'll get that off my calculator. So the p-value is much less than level of significance. So here we reject H null. We have significant evidence to say that the proportion of people on the south side is higher than the proportion of people in agreement on the north side. And we can say this is at the, well, I didn't specify a level of significance, so we're going to default to 5%, and that's fine. Now, just for curiosity's sake, or conversation's sake, what is the p-value associated with negative 4.2? Well, that is equal to, so if you're curious, the p-value is, how many zeros is there? There's 4 zeros. Doot, 1, 3. That's your p-value. Now remember, p-values can be interpreted as what if the null hypothesis is true. What's the chance of getting this result simply due to luck or random sampling variability? Well, what do we have here is tenths, hundreds, thousands, 10,000s, 100,000s, 13 chances in 1 million that this occurred due to luck or chance, which means unless it's a type 1 error, which is a remotely small possibility, then there is a significant difference between the north side and south side approval rates. That's it. Okay, let's move on. Okay, this brings us to the chi-square discussion. So we have a formula for answering questions, hypothesis test questions for single samples, and we have a formula now for 2 samples. But when you have multiple samples, you want to do 3 or more comparisons in one computation, this is your go-to method for now, chi-square. Formula for chi-square is, as you see here on the screen, it's the difference between the observed frequencies, or counts, and the expected frequency. You square away the negative. Of course, that gives you a result that's dimensionally too big, so we divide out the expected frequency, and it'll give you a value. And you got to do this for each category and for each combination of category and variable. So that's why we have to add them all up to get the final result. What are the 3 tests? Well, the first test is the goodness of fit test. And then we have the test for independence and the test for homogeneity. You're saying, that's a lot of stuff. Well, mathematically, these 2 things are the same as far as the math goes. The only difference between the test for independence and the test for homogeneity is how you word the null and alternative hypothesis. That's it. Mathematics is exactly the same. So we'll see examples of both. Now, there are a number of differences with computations. For instance, expected counts. So for goodness of fit, where you have multiple categories but one variable, this will be the number of categories. Somebody's using a power tool outside. Number of categories minus 1. That'll give you your degrees of freedom. Why am I doing degrees of freedom first? I'm totally distracted by that. Sounds like a lawn edger going on out there. Expected counts. The expected count for goodness of fit is the total number of observations times specified percentages for each category. So I just use the percent symbol with a subscript of I. I will work out a couple of examples to show you how to do that. The tests for independence and homogeneity have the same formula for expected counts. So for here, I'll do expected frequencies. This will be the row total times a column total divided by the grand total. So these are a bit tedious if you have a large sample set, but that's where software comes in. And I know some people say, well, if everything's done with software, why am I learning how to do this by hand? Well, at the end of the day, if you know how to do it by hand, you probably then become aware of how things can go wrong. The question really comes down to how do you know you have a right answer or a wrong answer if you don't know how to compute it by hand? Now, what do we have going on here? One moment, please. I'm going to have to mute my microphone for a minute. My apologies for being away. We had a little kitty emergency there. And so far, so good. Anyhow, a kitty emergency. If you're a cat owner, you probably know what I'm talking about. What do you mean you're barfing there? No barfing zone. Okay, whatever. Now, there's a caveat that goes with this these expected counts. You're going to see an example of this. When we do an expected count, you need a minimum of 5. A 5 minimum for a particular cell. If you don't get that, what you can do is combine the cells, the category that's deficient with one that makes the most sense logically to do that, and then proceed. That's one way to do it. Typically, it's the way we teach it. And there's other ways to do this. If you study more statistics, you'll find that the toolbox is very full of tools, but you can't learn how to use them all at once. So keep that in mind. There's an example of that coming up, by the way. Now, let's look at this degrees of freedom thing. I'll move this up a little bit. Okay, degrees of freedom. DF, for goodness of fit, is the number of categories, or columns usually, minus 1. Degrees of freedom for the independence test and the homogeneity test will be a bit more complicated, not terribly so. So degrees of freedom here will be the number of rows minus 1 times the number of columns minus 1. And you'll see that. Of course, we're going to do a couple of examples of these, so you'll get to see how this works out. Now, what's the curve shape? What does the distribution look like? Well, there's not just one. The curve changes shape as the degrees of freedom change. But in general, let's just do this. This starts at 0. This goes to infinity. And in general, we can say it has a right tail skew. So that means the rejection region will always be the right-hand tail. So this is where we're going to reject H null. So this will be chi-square. And this will be a critical value. So this is chi-square's critical value. It marks off the appropriate region for rejection, whether it's at 5%, 1%, 10%, or whatever you have. So that means if we have a calculated chi-square, sometimes it's referred to as the obtained chi-square. If it lands in that rejection region, you reject H null. This is the fail to reject region. So a chi-square value calculated or obtained, landing over here, is a failure to reject. So just keep that in mind, because this is our first encounter with what's called a cutoff table, where we don't have a large collection of p-values, but we do have a large collection of critical values. So that's where we're going to introduce the idea of cutoffs for significance. All right, so there's the basics of this. let's do some examples. Let's make some room here. Not that tool. Let's use this tool. Boom. All right, so this is an example from an old textbook. I changed the numbers because I don't remember what the original counts were because it's a long time ago. But the question really came down to, oh, hello, Kayla Astronomy. Welcome, welcome. Glad you could join us again this week. I'm just replying to Kayla on the chat today. So are World Cup class soccer players born or made? So this is the old nature versus nurture question. Canada, of course, the sport's hockey, although growing up was gradually transitioning to soccer even in the 70s. I remember playing soccer. It wasn't the big sport as it is now, but it's come a long way. So a great athlete, is that greatness inherent? Or can you teach someone to be great? Well, that's what we're going to find out here. That's what the thrust of this study was all about. How am I, Kayla? I'm doing fine. It's a lovely day in the neighborhood. I don't know where you're located at, but I know we had a air quality alert. So I'm in Alberta, and we're about 54 degrees, almost 55 degrees north latitude. So we're right on the edge of well, it doesn't look like it around here. We're still in what the biome is called aspen parkland, but we're not all that far from the boreal forest. And the fire season has already started. We've already had smoke alerts, air quality alerts going through again yesterday. Hoping we're not going to have a terribly smoky summer, and by extension, I'm hoping that people can actually go back to their homes. There's a couple of communities, one fairly large community, two in this province, have already been evacuated due to threatening wildfires. So thoughts are with folks in that situation. That's a terrible, terrible thing. Because when those fires come through, man, they just rip. The wind gets behind them, and it's a terrible thing. Anyhow, weather's pretty good here today. Wind's not too strong, and it's not too hot. Let's take a look at this question. We have observed counts for spring, summer, fall, and winter. The numbers I've listed here total to 400. So this is big N. So one of the first things we want to do then is let's write the hypothesis. What's the null hypothesis for this? Now, we could write the symbols for proportion for spring is the same as proportion for summer, for proportion for fall, for proportion of winter, but this is a goodness of fit test. I didn't write that down. Let's do that. So this is goodness of fit. Give this thing a title. Boom. Dear, I hope they can get that under. Yeah, a lot of people do. What we really need, back to the chat again for Kayla, is that we need rain. One of the things that you find if you go walking in the bush is the amount of deadfall. And let's face it, wildfires are nature's way of cleaning house. They burn it all out. And if it's a region with a lot of deadfall, a lot of dead wood, a lot of ground clutter, once the fire gets going in that, it's pretty hard to bring under control. Anyway, back to our hypothesis here. So I'm going to talk about this in context of, does the data fit? Do the observations fit the expected values? So here we're simply going to say the null hypothesis is that the data fit the model. And you're saying you haven't told us what the model is. Well, I'm going to get to that. I'm going to do that here in a moment. The alternative then is the data do not fit the model. There we go. Now, if you recall, let's go back here so you see what I'm talking about. And if you recall, I said for the goodness of fit that we need big N, total number of observations, times a given percentage for each category to get the expected value. But I didn't give you any. Hey, it's Rushback99. Welcome, welcome. Hi to you too. That's hi is typically a greeting for First Nation Canadians. So when you say hi, it's basically saying hello. So I didn't give us a percentage. N times percentage expected. Here we have to think between the lines. Are World Cup class soccer players born or made? The observed counts from this study were broken up into the seasons, spring, summer, fall, and winter. Although I suppose you could break it up into twelfths if you wanted to. But the point is, if you can teach greatness, then it wouldn't matter what season of the year you were born in. So we would expect, because I'm cutting the year into quarters, then we would read between the lines, think between the lines, that there would be 25% in each season. So watch out for that, because that has been an exam question. I've seen the context is different, but the idea remains the same. Now, that's easy enough to come up with an expected count. So the expected counts then, 25% of 400 is easy. That's just 100. So that's what we're going to put in here. There we go. Now we're in a position where we can actually compute the test statistic. And of course, that's this bad boy right here. So we need the sum of the observed frequency minus the expected frequency, square away any difference, and square away the negative signs, so some of them will be negative, and divide out the expected frequency. And then we add them up. So let's do that. And because we're squaring it, if you get it expected minus observed, who cares? It's still going to work out. So here we have 130 minus 100 squared, and we're going to divide that by 100. That's going to give us a value. So that's for the first one, for spring. Then for summer, we're going to have 120 minus 100. Square that, divide by 100. Then we're going to have, okay, I'm going to running out of room here. Let's move this up a little bit. There we go. Then we're going to have 80 minus 100 square, divide by 100. Okay, I'm not sure what the hell that is. Okay, it looks like 100 now. And then finally, we have 70 minus 100 squared, divide by 100. Now, Rushback, you're in Switzerland. Have you had any? I'm going back to chat with Rushback on the chat here. There was the big mountain slide in Switzerland. I saw that on the news recently. Has there been any change in the status? I'd heard that there was only one person missing. Is that still true, or has that been updated? We'll wait for him to get back to us on that. Let's look at our numbers here. 130 minus 100 leaves a difference of 30. 30 squared is 900, and 900 divided by 100 is 9. Here we have 120 minus 100, so that squares to 400, and divide by 100, that's 4. This will be the same, and this will be the same. I didn't actually choose the numbers to make it work out that slick. It just happened to work out that way. Because usually you get a decimal with this stuff, but not today. This should work out to 26. So chi-square is equal to 26. And that's a huge value. What are the degrees of freedom? Degrees of freedom are the number of categories, so spring, summer, fall, winter, minus 1. So we have, and it doesn't matter which 3 we choose, but there's our 3 degrees of freedom. We'll write this. Now, let's find out. No, everyone is okay now. Ah, good. I'm glad to hear that. Thank you, Rushback. Now, let's look at our degrees of freedom. So this is what's called a cutoff table. The numbers here, the entire table for the most part, is made up of critical values. The only p-values are in this row here at the very top. Let's look at row 3, because degrees of freedom 3. And we're asking ourselves, where does our test statistic land? Well, you'll notice in row 3, actually the trend for all of these is it increases as it moves to the right. So 26 is over here somewhere. Well, that means our p-value, I'm going to change this around a little bit. Interpret that then is we also notice the trend with the p-values. The p-values are getting smaller as the test statistic gets bigger. And that's how almost all of these tables work. Our test statistic is very large, which means our p-value then is very small. This relationship between test statistic and p-value is the same throughout this entire course. Large p-values give large test statistics give small p-values. So, what do we know? We have a p-value that's less than 0.01. So even if I were to set alpha at 0.01, our p-value is smaller than that. So then we can reject the null hypothesis. So here we would summarize by saying at the 1% level of significance, we find there exists evidence that the data do not fit the model. Now, I suppose we could reword that, I guess, in context of World Cup class soccer players born or made. Well, the null hypothesis suggests that you can teach someone to be great, but there's no difference. But there is a difference. The difference lies in spring and summer being greater than fall and winter, so it apparently, according to the numbers I've used here, that the time of the year you were born will determine your athletic ability when it comes to playing soccer. How much truth there is to that, I don't know anymore. I should really look up that paper again. It's out there. I have to look it up. So that's the goodness of fit test, with the complicating factor of they did not give you directly the percentages you need to compute the expected value. You had to think between the lines to figure it out. So how does it look when it's not the case? Well, that's what this example is all about. Let's look at this one. So now, let's move this around a little bit as well so we got more room to work. There we go. Certain organisms can be described by common characteristics. Particular single-cell organisms expected to exhibit traits with the following percentages. And I'm not being specific here, but we have A is expected to make up 0.25 or 25%. B is 60%, and trait C should appear 10%. I'm kind of hinting around at, some of the genetic analysis. Anyway, the point is this stuff better make 100%. It's always wise to check that, of course. Now, what do we observe? We observe a frequency of 70 appearances of trait A, 200 for trait B, and 30 for trait C, for a total of 300. Is the observed trait frequency consistent with what we expected to see? Well, this is a goodness of fit test, where I have given you the expected percentages. We just need to come up with the expected values now. So again, the null hypothesis is that data fit the model. And the alternative is they do not. Data do not fit the model. And I haven't worked this one out ahead of time, so I don't know what level of or what the result's going to be. So we're going to set this at 5% and see what we get. All right, so let's get expected values. The expected counts. Okay, so for category A, I need 25% of 300. So this would be 0.25 times 300, and that's 75. So the observation 70 isn't terribly different than 75. Now, we need 60% for category B, and 60% of 300, well, that's 180. So that's 0.6 times 300, so this is 180. And then finally 10%, oh, that's easy enough. That's exactly 30, and we have 30. So we go 0.10 times 30, and we get 30. That's how we do that. Let's calculate chi-square. So chi-square, I didn't put the formula on here, I didn't have enough room, so I'll just write it here. Chi-square is going to be the sum of the observed count minus the expected count, and we're going to divide out the expected count. And we have to do that 3 times. So here we have 75 minus 70. I got that backwards. It doesn't matter as long as we have the expected count in the denominator. So this is 75. So that's backwards, but I'm not going to... Well, you know what? I don't want to mess anybody up, so let me fix that up. So this was 70, and this is 75. Okay, there we go. Now, here we have the observed was 200. We're going to subtract 180. We'll square that and divide by 180. And I'm going to wedge this one in here anyway. So here we have 30 minus 30 divided by 30, which of course is 0. All right, 70 minus 75 is negative 5. Negative 5 squared is 25. 25 divided by 75 is 1/3. We're just going to write 0.33. Over here, the difference is 20. 20 squared, that's 100. What am I saying? That's 100. That's 400. And 400 divided by 180, well, that's going to go twice, and that should be 2.22. That's 2.22? Yeah, that's right, because that's going to be 2/9, right? That's the leftovers. We've got 2/9. Yeah, that's right. So this is 2.22 plus 0. So our test statistic chi-square is 2.55. And the degrees of freedom again, number of categories minus 1, so we have 2 of those left over, so we have 2 degrees of freedom. Now let's take a look at that little table down here. We're using row 2 this time, and our test statistic is 2.55. So 2.55 is smaller than 4.6052, which is the smallest given value in the cutoff table. So that means our p-value then is greater than 10%. Easy enough. So this is a fail to reject. We can say, since alpha is greater than the p-value, it's supposed to be a v, by the way, we fail to reject. So the data is consistent with the model. Now, just as a for instance, let's say that, let's do a quick example here. Let's say chi-square on 2 degrees of freedom was 5.5. Then what we would do is we would come across here until we find the region where 5.5 lands, which is right between those first 2 columns. Then we'd go up here. So this is how you use, I'm just going to grab my eraser and get this circle out of the way here. So here's how you would do this. So in the example of 5.5, we could say that the p-value then lands between 10% and 5%. And really, we don't need to know what the exact p-value is. We just need to know how it relates to some level of significance. And these are usually typical levels of significance values in this column, or that row, pardon me. So I have a couple more examples to do, so we'll see some more of this. Let's move on. Okay, we're going to move on now to the test for independence and test for homogeneity. So let's write that. This is test. This one specifically is for independence. And how do I know that? No, it screws that up. Brain. What is that? What's a brain? I don't know anymore. So here I'm seeing, is the choice of evening recreation associated with gender? So that's another way of saying, is the choice of evening recreation independent of whether someone's male or female? So oftentimes they're not going to specifically say to you, is there a dependency, or are these things independent, because that's just making it too easy. So they use another word, and the common word is associated. And that's what this question's about. So how do we do the null and alternative hypothesis for this? Let's do that. H null is that evening recreation is independent of whether you're male or female. Hey, 17 to the square followers. You're right. Did we hit 289? Awesome. E to the 2 pi. Thank you. See, it didn't take me too long to figure it out. E to the 2 pi just joined us on the chat. And yeah, I'm a bit of a number nerd. I like my squares and cubes. Thanks for picking up on that. Actually, Adrian's even more so of a number nerd, but sometimes he misses those. I think he's got a little brain glitch or something. I had to clue him in that 18 squared was 324 the other day because he couldn't do it. And I'm going, Adrian, your mathematical abilities are beyond measurement, yet 18 squared isn't what you said it was. I put that as a feather in my hat, by the way. Anyway, getting back to this, the H null is that evening recreation is independent of gender, whether you're male or female. H null is always going to be the opposite. So remember, the null hypothesis is there's nothing special going on, hence you're independent. And the alternative must be a dependency. I'm not going to write the whole thing again. I'm just going to say a dependency exists. Ooh, there we go. Well, whatever the level of significance is, we'll figure that out later. Now, we've got to do a fair bit more work to answer this question. We need expected counts. And if we go back here, not that one, and not that one, the expected count for test for independence or test for homogeneity is this thing here. We need the row total for each cell times the column total divided by the grand total. So for instance, if I'm going to use red ink here to write the expected counts. So this is the row total, and this is the column total for females in knitting. So we're going to have 35 times 17 divided by 70. This is your grand total. Now this works out, I've made these numbers to work nice. You'll notice that, remember that order of multiplication doesn't matter. So if I go 35 over 70 and then times 17, that's the same as saying, well, that's just a half of 17. So here I've set this up so that you can, if you don't have a calculator, you can still do it. So what is half of 17? Well, it's 8.5. So the expected count here is 8.5. Now, regardless of whether it's the expected or the observed, it still has to add 17, so this has to be 8.5 as well. We also know that that works because this is also 35. We have an even split between male and female, so we better see that even split in the expected counts here as well. Now let's do the same thing with cards. So cards and females. So now we have 35, but this is 21 now, times 21, and this is, of course, divided by 70. So half of 21 is 10.5, and this is 10.5. So the math doesn't have to be terribly hard here. Doesn't, it's not going to be super slick and easy all the time. I make numbers to work out. So doing the same calculations here, you'll see that this column totals to 25, and it has to be a 50-50 split. So this is 12.5, and this is 12.5. Here this adds to 7, and this is 3.5, and this is 3.5. And now we run into a conundrum, also known as a problem. Let's go back. I want to remind you of something I showed you earlier. The minimum expected count for any cell has to be 5, and we are too small. Now, how do you handle that? Well, that's what we're going to do in this example. What you do is you combine. So here we have categories for recreation: knitting, playing cards, watching Netflix, or simply chilling. But this is too small. So, of course, it only makes sense then to combine Netflix and chill into one. Huh? How about that? See, I made a joke here, okay? Anybody? Joke? We're going to Netflix and chill for the third column. Come on, people, I need a little love here. Give me a chuckle or something. All right. Don't laugh at your own jokes, Tim. Okay, now we have to recompute. Well, the only things we really have to recompute is this last column. So let's do that. So this is still 8.5, and this is 8.5. This is 21, so half is 10.5 and 10.5. I'm not getting any love here in the chat for my joke. Okay, 32, that makes this 16 and this 16. Okay, there we go. Now we can do this. Go back to a different color, blue. Okay. The expected counts are now done. Now we can do the chi-square. Now there's 6 computations here. Now one of the things that's going to make our life a little easier here is because the sample sizes for males and females are the same. Whatever I compute for female in knitting or female in cards or female Netflix and chill, we're going to have the same contribution towards chi-square for the males. So I really only need to compute the first row and times it by 2. And the only reason I can get away doing that is this thing and this thing are the same size. Let's do this. Okay, so chi-square. So here we had an observed value of 10. We are expecting 8.5. We'll square that, divide by 8.5. So this is 1.5 squared, which is 2.25 over 8.25. Why am I doing that? Control Z. Thank you. All right, so calculator. Do I have enough battery power left here? Are you even going to turn on? Come on. Oh, yeah. There we go. 2.25 divided by 8.5 is 0.2647. Okay. Now let's look at the next one. So this is going to be 8 minus 10.5 squared divided by 10.5. So the difference there is 2.5 squared is 6.25 divided by 10.5. Critical battery, yeah, I know. And we get 6.25 divided by 10.5, and that's 5952. And I'm going to try and get the last one in here before my calculator checks out. Here we have 17 minus 16 squared, and divided by 16, so that's just 1 over 16, which should be 0.0675? No, it's something, Batman. 625? Let's find out. 1 divided by 16 is, 0.625. Okay, so I'm going to add these up. So that plus 0.5952 plus 0.2647 is 9224. But because of the fortunate circumstance of having equal sample sizes, I can times that by 2. I'm going to move this picture out of the way for a minute. Times 2. So this is going to be 1 point something, 1.848. There's our degree. Now, there's our test statistic. Now, what's the degrees of freedom? Our degrees of freedom, again, from our earlier discussion, is the number of rows minus 1 times the number of columns minus 1. So that leaves us with 2. Here's an easy way to get that, by the way. If you have a table in front of you, if you strike out 1 row and you strike out 1 column, you have 1, 2 left over. That's why we have 2 degrees of freedom. Now, there's our degrees of freedom, 2. Problem, of course, is that 1.8 is over here somewhere, and that means our p-value is bigger than 10%. What's going on here? Somebody's being fussy. Come on, let's put that to the top of everything. There we go, that should do it. Boom. So we had still messing up. Okay, whatever. Anyway, our p-value is greater than 10%. So that means we fail to reject H null. Now let's go previous. Remember, we suggested that the null hypothesis is that evening recreation is independent of gender, and we don't have any evidence to dispute that. So it seems like males and females basically prefer some combination of knitting, cards, and Netflix and chilling for evening recreation. Let's look at another example. This will be the test for homogeneity. Now, homogeneity means even distribution or proportional distribution. I like to use the word proportional because I find it's there's one specific example when you say things are equal. Well, what do we have here? Let's look at this. I have 40 men and 60 women, which means we expect 40% of the observations to be male and 60% to be female or women, right? So if the observations match that, then we can say that we have proportional distribution. And if they don't, well, then we reject that hypothesis. So let's set this up. And why is that doing that? There we go, that's better. Okay, so the null hypothesis for this is that we have proportional distribution. The alternative is that it's not or non-proportional distribution. Everything remains the same. Mathematically, the test for independence and the test for homogeneity are exactly the same. So let's do that. Let's see what we get. Now, ooh, that soda might be a problem here. No, I think it'll be fine. Okay. So remember, expected counts are going to be, let's write this down, expected frequencies, same thing. That's going to be a row total times the column total divided by the grand total. Grand total being 100, so that's going to make this easy. So let's look at the first cell. Let's use red ink again. So for men and wine, the row total is 40, the column total is 35. So we have 40 times 35. Grand total is 100, so that makes this really easy to do. So 40 times 35, that's a, what the hell is that actually? That should be, well, what's 40% of 20? No, 40% of 35. I know, let's use the calculator, because why not? All right, please don't go dead on me. So we have 40 times 35 gives us 1400. So this is 1400 divided by 100. So that means there should be, we were expecting 14, we observed 20. Now recall what I said in the previous example, whether it's observed or expected, they still have to add up to the column total. So if I have 14 there, and I have to have a total of 35, then this has to be 21. In other words, this went down by 6. This has to go up by 6. Cool. All right, moving on. Let's go over here now. Let's do this one. 40 times 45 divided by 100. So what is 40% of 45? Well, that should be 18, but let's check. Here we have 40 times 45 should be 1800, and it is. So this works out to 18. So this one went up by 3, this had to go down by 3. Otherwise, the math doesn't work out. Now let's go over here. Here's 20. So now I got 40 times 20, that's 800, divided by 100, so this is going to be 8, and that means this has to be 12. There we go. So we don't have to be totally reliant on calculators to do these things, although it helps. Now, let's figure out our test statistic. Now, I have to do this. There's 6 cells, and we do have to do all 6 this time because the row totals are not the same. We need a little bit of room. Okay, what do we got? So for the first one, we have 20 minus 14 squared divided by 14. And then we're going to have 15 minus 18 squared divided by 18. I'm really writing large here today. Moving on, move this up some more. Whoops, come on. Not that one, this one. There we go. And then got 5 minus 8 divided by 8. So that'll be the top row. So difference is 6. That's 36. 36 over 14. Yeah, you know, I should be able to do that. That's the same as 18 over 7. Yeah, you know what? I know what 7s are as far as decimal goes, but we're just going to do the calculator work. It's 2.57. 2.5714. Now here the difference is 3. 3 squared is 9. 9 over 18 is a half. That's easy. Cool. Here's the difference of 3. 3 squared is 9. 9 over 8 is 1.125. There we go. All right, so that's the men row. Now we got to do the women row. So now we're going to have 15 minus 21 squared divided by 21. And then we're going to have 30 minus 27 squared divided by 27. You see the differences of the denominators, right? And then we have 15 minus 12 squared, and then we have 12. Boom. Okay, figuring this stuff out now. So the difference there is 6. It's 36 over 21. And that's going to be 1 and some change, but I'm not going to try to do it in my head because I'll just screw it up. 21, 1.714, 2. There we go. Here we have 9 over 27. That's a third. That's easy enough. That's just 0.33. And here we have difference is 3. 3 squared is 9. 9 over 12 is 0.75. There we go. All right, if we sum all of these, what do we get? Let's find out. Plus 0.333, 3 plus 0.75 plus 2.5714 plus 0.5 and plus 1.125 gives us a test statistic of 6.9940. Now, what's our degrees of freedom? Same as last time. It's the number of rows minus 1 times the number of columns minus 1. So if we strike out one of these and one of those, we have 2 degrees of freedom. Let's look at row 2. Here's row 2 right there. Now, where does our test statistic 6.99 land? I'll try my marker. Maybe it won't go blank. So 6.99 lies between these two values. It's still blanking out. It doesn't matter. Anyhow, that means the p-value. So if this is where our test statistic lies, then our p-value has to be smaller than 0.05, but bigger than 0.025. So p-value is greater than 2.5%, but smaller than 5%. So if I was to set the level of significance, let's say alpha was at 5%, that's our default value, this gives us evidence to reject the null hypothesis. We can say that the distribution of libation preferences is not proportional between men and women. So this is a reject H null conclusion. Otherwise, the mathematics, as I said before, is exactly the same. It's just how you word the hypothesis. I got one last thing to do here, and then we're going to wrap this up. There's an interesting little computation that shows up. I know it's one of the favorites around the university I hang around, is you can convert the chi-square value to a z-score, provided you have a 2x2 table. And remember that when you get the p-value, that it's a two-tailed p-value, so we have to convert. Or when I say convert, I mean multiply by 2. Well, so here's the table. Let's do a quick and dirty computation. What are the expected counts here? Because we're just going to blitz through this because I want to concentrate on the conversion process. So we have 30 times 30, which is 900, divided by 65. So 900 divided by 65, I should know that one. Let's just do the calculator. No, that's not what I thought it was. But anyway, it's 13.8. I'm only going to use one decimal because the point of this example is to illustrate the conversion. So that's 13.8, and it still has to add to 30. Then this has to be 15, no, not 15, 16.2. There we go, that makes that. And then over here, I've got 30 times 35 over 65. And what is that? 30 times 35 divided by 65 is 16.1. So if that's 16.1, and I subtract that from 35, I get 18.2. So this was 16.1. Now, what is chi-square? So chi-square, quickly, is going to be 3.8 squared divided by 13.8. And then we're going to have another 3.8 squared. This time divided by 16.2. I'm just going to do it all in one string on my calculator if you're wondering what's going on here. I got something wrong here. This isn't right. 18.2 can't be right. It's got to be 18.9. Is that right? Yeah, that's right. This should have been a 9. Something didn't look right, and that's what it is. You write down the wrong number, you're going to get the wrong answer. All right, so that's 3.9 squared divided by 16.1, and then we're going to add, difference here is 3.9 squared divided by 18.9. So quick and dirty chi-square is 3.687. 2. So here's how you do the conversion. Chi-square is simply z squared. So the square root of chi squared then is going to be the square root of 3.6872. And what is that? 1.92. And this is our z value. Now, what's the p-value associated with that? Well, let's check something. So here's 3.6. Degrees of freedom is 1, by the way. df is 1, because remember, we're going to strike out one of these and strike out one of those. That's all we got. So on 1 degree of freedom, 3.6872 is in this region. So this says the p-value for chi-squared, p-value, is less than 10% greater than 5%. Now I'm just going to use my calculator. I don't have a z table handy, but we're going to quickly get the p-value for our z-score. Our z-score p-value, so for z-score, our p-value is 0.0274, but we have to go 2 times the p-value, and we get 0.0549. Well, 48 and then some rounding, whatever, good enough. So you'll see that this is consistent with this. And that's how you do it. So to convert chi-square to z, you square root chi-square, and then go 2 times the p-value from the z table. And that's it. Okay, that was a long session today, I admit that. I wanted to get this all done so we can move on to mean values. So that concludes lecture number 13 for our Introduction to Statistics, hosted by Willa today. That's our mascot. Willa is, as you can see, a floofy cat. She's a medium long hair, not a full bush. And she's a tux. Pretty sexy kitty. I like her. And Willa lives with Adrian, who's also part of our Tutor Wizard Triumvirate, and we also have Lorenzo. I didn't see Lorenzo on the chat today, but that's okay. He's probably busy. A lot of folks are doing stuff when the weather's nice. Thank you for joining us for this. I know I've done 3 of these lectures just back to back, back to back, back to back. I'm probably going to take a day or two before I start looking at the corresponding discussions, lectures for mean values, but that'll be a couple days down the road. We'll get there. So you probably had enough of this. I'm going to say thank you again, and we'll catch you on the next stream. Now, before I bail though, I do want to try and do the RAID thing. I haven't managed to get this RAID thing to work because I'm a bit of a, well, I'm not technologically uninclined. I'm just sometimes technologically, what's a good word? Technologically not challenged. Forgetful. That's the right word. I'm technologically forgetful. Let's search for math. Let's see if Don does math, see if he's around today. Maybe we can do a handoff for that. Let's see what we can do here. Aero Engineer, hey, have a good one. Thank you, Aero Engineer. Appreciate the good wishes. Now, okay, now you can clearly see I need to reboot this laptop. It's been running for the better part of a week, I think now, and memory's a little, I'm on you. Probably need to recover some memory here. All right, what do we got going on here? Who's in attempting math? My purpose in life. We have that. Smile. I'm not on camera. So who do we have here today? We don't. Oh, okay. So looks like we have 2 people doing math today, and we have trash room, speed running algebra. And we have attempting math. Now I know there's another filter I wanted to try, which was math is fun. Let's see if we can do that. And math is horror. No, no, no. Math is fun. Let's try that. Nothing. Okay. You know what? Let's see if Don does math. Well, no. Can I search on that? Let's try. Don does math. I'm open to suggestions, by the way. If somebody knows a math channel that's currently streaming, I'd be happy to. No channels found. Okay. Nuts. All right. I'll go back over here. We're just going to do the math. And moth. Yes, let's go find some moths. Boom. Math. And looks like we're going to raid this one. Okay, stream chat. Cool. There we are. So, got it. All right, stream preview. There we go. So, there we go. Oh, their Femvox fan is on that one too. I picked a good one. So let's do that. Start raid. Oh, Dawn just ended. Okay, I'll catch him next time. Okay. 6 viewers raiding in 1 minute and 16 seconds. Okay, let's raid now. So I'm kind of new to this Twitch thing with the rating of channels and things, but we'll get there. We'll get there. Oh, my laptop is slow today. It's the ubiquitous lag. I'm thinking it's time for a reboot. Okay. You should be going on there. How come this is not picking up? think I'm crashing too. That's not good. Academy of Useless Ideas. That's a great one. Okay. Come back over here. Whoops. That's not what I wanted to do. Sorry. My bad. My bad.